this video, I'm going to go over how you determine if a molecule is polar or not polar, and that's really, really key for everything that comes after. So when we talk about polarity, polarity means that I have a negative region and a positive region in the same thing. So if I have a polar bond, there's a negative region in the bond and the positive region in the bond. So if I have like hydrogen bonding with fluorine, for instance, well, fluorine is highly electronegative, so that means it pulls the electrons to itself and it pulls it away from the hydrogen, which creates a negative end on that fluorine. Well, a molecule can also have this. So you have a negative region within the molecule and a positive region. Okay, so when we look at a bond being polar or not, the electronegativity difference has to be greater than 0.4. So I'm just going to say this, you're not going to get that table of electronegativities. So if you see that you have two nonmetals bonding together, most of the time it's going to be polar, except for a few instances where you know it's definitely nonpolar. Carbon bonding with hydrogen leads to a nonpolar bond. And then also anything that bonds to itself. If I had oxygen bonding with oxygen or fluorine bonding with fluorine, that's going to be a nonpolar bond as well. Okay, so when we have those polar bonds, we have something called a dipole moment. So that is the direction of the negative region. So where are the electrons being pulled within the bond or within the molecule? So the arrow is going to show us where the electrons are being pulled. So if I'm having this molecule right here, the chlorine is pulling those electrons over towards it, which leads to this partial negative end and a partial positive end. All right, so a molecule, whether it's polar, really depends mostly on its shape. Now, if you have polar bonds within the molecule, that can lead to a greater degree of polarity, but really and truly this is going to depend on the shape. You're looking for an asymmetrical shape for it to be polar. Okay, so nonpolar molecules are going to be symmetrical, okay? So the dipoles will end up canceling each other. So I want you to think about a dipole like a vector, okay? So what we do with these vectors is we add them together, and then if we get something that's not zero, it's going to lead to a more negative region and a more positive region, okay? But so when you look at the molecule itself, you're looking to see, do you have something that's equal and opposite? So if they're going in opposite directions, so let me kind of show you. Okay, so this right here, this is a molecule that is symmetrical. So we have dipoles going out towards the fluorines here, and then if I were to take these and then I added them together, I would end up with a net zero dipole. Okay, so when you look at this, it's harder to tell a little bit with this, because what you have to do is, well, these are going down, okay, which will counteract the one that's going up towards this fluorine right here. And then you have one that's going to the left and one that's going to the right. Now, if I really wanted to, I could use trigonometry to solve for this, and then I would end up with a net dipole of zero, but that is beyond the scope of this course. So I'm going to tell you which shapes are going to be symmetrical. So the shapes that are symmetrical, that's going to lead to a nonpolar molecule. Okay, so polar molecules are not going to have the dipoles cancel out. So right here in this particular molecule, you have an oxygen and a hydrogen. Well, technically the dipole would be going towards the oxygen, and then it ends up being that it's all going net towards the oxygen. So you have a net dipole going towards the oxygen, so that means that you have a negative region around the oxygen and then a slightly positive region around the hydrogens. Okay, so here are this is the general guideline to tell if something is symmetrical or not. So the symmetrical shapes, linear, trigonal planar, trigonal bipyramidal, tetrahedral, octahedral. All of these lack lone pairs on the central atom, okay? There are two down here that do actually have lone pairs, okay? So square planar and T-shaped, and what ends up happening with these particular shapes is because, remember, the lone pair is repelled more strongly with a square planar. I actually have all the 4 atoms sitting in a one plane. So let's say that I have a central atom here, and then I would have one like that. You end up with a lone pair directly on top of that central atom and then directly on the bottom. So it ends up canceling, okay? Same thing for the T shape. You end up with trigonal planar in the middle, and then the 2 lone pairs are going to be directly above and below the central atom. Okay, so most of the symmetrical shapes lack lone pairs on the central atom, except for these last 2 down here. The asymmetrical ones, bent, trigonal pyramidal, T shape with 3 lone pairs and 3 bonding pairs, square pyramidal, and then the seesaw shape. Okay, these all have lone pairs on that central atom. So really, if you draw your Lewis structure and you see lone pairs on the central atom, more than likely it's going to be a polar molecule because it's asymmetrical. All right, so polar molecules have asymmetrical shapes, or we could say the atoms are different. So if I have this right here, I have 2 hydrogens and then a fluorine like that. Okay, so if I have this molecule right here, this is a tetrahedral shape. There's 4 atoms bonding to that central atom. However, you've got 2 fluorines and 2 hydrogens. They all have to be equal, okay? So it is going to be an asymmetrical molecule, so it's going to be polar. Now, if you look at this and you're like, well, it looks like everything is symmetrical here. I've got one of these fluorines here, one of these fluorines here, hydrogen here, but you have to remember this is a 2-dimensional drawing, not what the 3-dimensional object would look like. If you actually build this molecule, you would see that the fluorines end up being clustered in one direction and the hydrogens end up being clustered in one direction too. So it is asymmetrical. Polar molecules, if you have polar bonds, that leads to a greater degree of polarity, but really we're going to be checking for that asymmetry first, and then if we've got polar bonds, it leads to a greater degree. Okay, so let's do some examples. So first thing, you have to have your Lewis structure. So for the love of all that is holy, make sure you're counting to see how many electrons should be in that Lewis structure. There should be no more, no less. Hydrogen has 1 electron available for bonding. There's 2 of them. Oxygen has 6, so there should be a total of 8 electrons. No more, no less. Oxygen's in the center. Draw your single bonds to your hydrogens. Hydrogen never gets dots, and then the leftover electrons go on the central atom as lone pairs. So when we look at this, we have 2 lone pairs, 2 atoms. That is going to be a bent shape. Automatically, I can look at this and say, oh, I've got lone pairs on that central atom. That is going to lead to asymmetry, so it is polar, and it's highly polar. Hopefully we do remember this from bio. All right, so carbon has 4 electrons available for bonding. Hydrogen has 1, and that would be a total of 8. Hydrogen or carbon in the center. That's 6 electrons, and then that's 8. Okay, so that would be a tetrahedral shape. 4 atoms bonding to that center. All the atoms are the same, and it's a symmetrical shape, which means this is going to be nonpolar. All right, OF2. So there should be a total of 20 electrons. Oxygen in the center, fluorine. Make your single bonds, and then draw lone pairs, or distribute the electrons to the outside atoms. There we go. We've got 4 more electrons, so they go on the oxygen as lone pairs, which means we again have a bent shape, which leads to a polar molecule. And I2, if you don't even need to draw this, it's 2 atoms bonding to each other. They're the same thing. That is going to be a non-polar molecule. All right, so let's look at this, SO2. Oh, go back. Oxygen and sulfur both have 6. All right, so it's 18. Sulfur in the center, oxygen, oxygen. All right, draw your single bonds, distribute like that. I have 2 more electrons. They go on the lone pair, or on the central atom as a lone pair. Now, sulfur is not satisfied, so I'm going to pick one of these and make a double bond. All right, and then it has resonance because it can bond they can have the double bond here or on this side, so it's resonance, which leads to different kinds of bond lengths. All right, so we have a bent shape. All right, and then that's going to lead to polarity. All right, so CH3OH, okay, anytime you see this right here, okay, or it says alcohol, automatically know it's very polar, okay? But when we draw the Lewis structure for this, all right, we have hydrogen, hydrogen, hydrogen. Now, I'm not going to attach the oxygen and the hydrogen to the carbon because now that would mean I would have 5 bonds in the carbon, which is not possible. Carbon is on period 2. It's not capable of having an expanded octet. It has to be on period 3 or lower in order for it to have that expanded octet. So we would have an oxygen here, and then I can attach the hydrogen here. All right, so if I'm counting my electrons, that would be 3 for each of those, 1 times 3, and then I would have 6 and then 1. So that would be 9, 10, that would be 14 electrons. I only have 1, 2, 3, 4, 5, that's 10 electrons. So they would go on the oxygen as a lone pair. All right, so this right here, this is an alcohol. Alcohols are going to be polar. So when I look at this, this is not symmetrical. The carbon is not bonding to all 4 of the same thing. So that's going to end up being a polar molecule. And technically the shape is a little bit different because I have a carbon in the center and I also have an oxygen in the center. So it ends up that it's a chain, okay? So each one has a slightly different shape. So this would be the tetrahedral shape, this would be the bent shape, but really when you see this, it's hydrogen, 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 and then oxygen, which means it's asymmetrical here.